uniqueness. Okay. So what does that mean? So ax equals b has not more than one solution. Not more than one solution x in x for whatever b you try. I always find it easier to envisage the opposite property. So suppose this is not the case. So suppose there is a b over here for which you have two different solutions, x and x tilde. Let's say they both are mapped onto the same b under the operator a. So this is clearly not what we want. Okay, so not this situation. Still, let's start to understand this situation, and then we just take the opposite. What do we have here? Well, we have that ax equals b, but also ax tilde equals the same b, which must mean that ax equals ax tilde, or you get 0 if you take ax and subtract ax tilde. By linearity of a, so a is linear, you can write this as a of x minus x tilde. And what is this telling us? It's telling us that x minus x tilde is one of those vectors that, if you apply a to it, gives you 0. And this is what we call a vector in the null space, or in the kernel of a. So here we put kernel of a equal to the following set. It's the set of all little x's in x that are mapped by a into the 0 element of y, which is maybe somewhere over here. So you're asking who is mapped to 0, and maybe there's more than one element with this property, and all of these are collected in the set that we call the kernel of A. Okay. Again, this turns out to be a vector space. This time it's clearly a subspace of capital X. We call it the so-called kernel of A. Some people would say null space, which also fits very nicely because it's a space, and it's the space of little x's that are turned into 0 or null if you apply a to them. Okay, where did this come from? Well, it came from here. We just found out that the situation that we do not want is that for two different little x's, call them x and x tilde, the image ax and ax tilde is the same, or as we just saw, the different x minus x tilde is an element of the kernel of A. So if x and x tilde are different from each other, okay, so we have x not the same as x tilde, then this different would just not be 0. Okay? So the situation that we do not want is that there are non-zero elements in the kernel. Not non-zero elements in the kernel of A. It's quite clear that the 0 element of X is always in the kernel. Why is this clear? Well, it's mapped to 0. If you take a linear operator A and apply it to the 0 element, then you get the 0 element. Asking why this is so? Yeah, good question. Let's discuss it in the problem session in the afternoon. Okay, so let's summarize. AX equals B has multiple solutions X, which is the situation that we do not want, if and only if the kernel of A has non-zero elements. Okay, so this is the takeaway message from the previous slide. Now we are interested in the opposite, but that's easy to do. Just say has, just say has no multiple solutions X if kernel A has no non-zero elements. Or to phrase this differently, X equals B has unique solutions. Well, actually one should say has a unique solution, because there's only one. If you say unique, has a unique solution, if it has one, if and only if the kernel of A does not contain any elements other than 0, but it always contains the element 0, so it must be equal to the set that only consists of the 0 element. Okay, remember those words from Maths 1? Do you remember the corresponding word here? So this would be phrased as A is injective, right? Okay, and this is another big and important box. Excellent. Okay, you should read this sentence in the sense that A has a unique solution if it has one. So let me add this here. If it has one, if and only if A is injective. Well, that makes it sound quite complicated, but if it has one, that depends on whether or not this is in the image of A, as we learned before. Okay, if it's not in the image, then you have no solutions. Right, so you have 0 or 1 solution, but not more than that. This is what injectivity of A says. Let's come back to the situation of multiple solutions. How can I describe them? And I mean, we already found the result over here. If you have one solution X that gives you the desired right hand side B when plugging into the operator A, then you will find all the others, like this green guy, by just adding this difference, x minus x tilde or x tilde minus x. And what do we know about this difference? Well, we know it is in the kernel of A. So if you have a solution and you add something in the kernel, you still have a solution. And that's in fact easy to check, right? So if, let me call xp, because we say this is a particular solution. So it just means a xp solves the equation, x equals b. And if, well, what should I call it? If k is in the kernel of A, which means if I apply this, then I get 0, then particular plus k is again a solution, solves x equals b. Believe it or not, you can just check it, right? So you just take A and plug this in, xp plus k, and you get axp plus ak by linearity, which is, okay, so this bit is b, and that bit is 0, so you get b plus 0, which is of course just b. So indeed it solves your equation. And vice versa. So if you solve the equation, then you're of the form particular solution plus something in the kernel. This is what we checked earlier. So the set of all solutions of x equals b looks like this. Let me call it L. I'm used to the letter L because in German you say Lösungsmenge, so I still use L, hope you don't mind. So L is just xp plus k, where k is running through the kernel of A. Sometimes you just abbreviate this, so you just give it the following shorthand. You say take xp and add the whole kernel onto it. Again, you see lots of important formulas today. So the set of solutions is just one particular solution plus whatever you find in the kernel. Instead of kernel, you could say set of solutions of the homogeneous equation. Did you hear that before? Ax equals 0 is what you call homogeneous equation, right? Homogeneous equation. Right. Okay, let's bring a couple of things together. We saw a condition for unconditional solvability. Well, that sounds great. So whatever right-hand side comes along, you can always solve. That's good. That's surjectivity of A. And then on the other hand, we have injectivity, which means if you have a solution, then it's unique. So if you have both of them together, that's great. So you can solve for every right-hand side and you get a unique solution. Let me summarize that. So A is surjective. That means x equals b is solvable for every b. and A is injective if and only if solution X is unique if existent, right? Well, you clearly want both of them, and that's what you call bijective. So you say A is bijective if and only if it's surjective and injective. Let me just put a big and sign in between. So what I have to do is to put an and sign in between here. So you get solution always exists and is unique. Okay, so this can be characterized by the image of A being the whole of Y. This can be characterized by the kernel of A being just a set of zero elements. So here you would have both of them, right? So you have image of A is Y and kernel of A is just the zero element. If that's the case, then let's do another drawing here. So we have our sets capital X and capital Y, and no matter what element B you take over here, you always find an X over here, which is mapped perfectly onto B, and moreover, it's the only X. No other X would do the same job. This is the situation we've just described, which means bijectivity of A. You could understand that as, I mean, we say for every B there is exactly one X that solves the equation. So you could just map it backwards. So you could say, okay, for this B, I have a map that for this B gives me exactly the solution X. Do you know how you call that map? You just call it A inverse, right? So it's the inverse of A. It's the operator that takes you back from image B to the pre-image X, as you say. The inverse of A. And that's why instead of bijective, we like to say invertible. Okay, important. In fact, we say that more often than bijective. Okay. So the inverse of your operator A, we call, so A goes from X to Y, and the inverse, if it exists, goes the other way. It goes from Y into X, right? And this was a linear operator. Now the question is this one also linear? Yeah. Next question.